any questions about where we're going? Sebastian? So this might. I said that Wednesday, but I'll give you a little bit of a reminder. I don't know how much detail I'll go into right now, but basically something I asked you to do a while back was this. We looked at this function, the f of x equals the absolute value of x. Actually, the natural log of the absolute value of x. And we found a derivative of this thing. Or that was our goal. So if you'll recall, something else we've said about absolute value is that you can do this. We can break this absolute value into this piecewise function, where this is going to be equal to natural log of x when x is positive, and the natural log of negative x when x is negative. And keeping in mind that that function is not well defined if x is 0. So we can take the derivative of either one of these, right? Yeah. What's the derivative of natural log of x? 1 over x, right? And kind of tricky, what's the derivative of natural log of negative x? Also 1 over x. Because chain rule says this. What's the derivative of natural log of anything is basically it's 1 over that idea, right? But then chain rule says you multiply by the derivative of. This is one of the things we said about that was kind of, something that was special about this derivative here, natural log of ax. That's equal to 1 over x no matter what a is, no matter what real number a is. So because of this, basically what we have here is that basically what we've done is because really what's going on here is this f of x, f prime of x is equal to 1 over the absolute value of x. All right, so that's a good question there. Thank you for reminding me. I forgot I said I would give more detail on that. All right, so let's get into some more involved antiderivatives here. So I'm giving you the derivative g prime, and I want to find the general case for g of x. So you can deal with time. So what's a function whose derivative is 4 secant squared x? 4 tangent x. All right, how about the second term? Does that look like something you can take an antiderivative of? So I do not think that's something you can deal with, but I think there's a way you can get to something more digestible. Is there a way to rewrite that 2x to the 5th and so on? Okay, so do this one step at a time. 2x to the 5th over x minus radical x over x. And while we're at it, let's go one better. It becomes 2x to the 4th minus x to the negative 1/2. All right, so this down. All right, that rewrite there allows us to think about that that in terms of two smaller terms. So we have 4 tangent x. What's the antiderivative of 2x to the fourth? How did you get 2/5 x to the 5? Yeah, so, and that's essentially, I mean, these last two terms, we can essentially think of them as the, power rule of differentiation. So as long as we're bringing that up, what is the antiderivative of, so if f of x is equal to x to the n, I'll say keep the notation we had last time. What is capital F of x equal to? Oh, so that is if we're taking derivatives. We are taking the antiderivative. So basically, I want the function derivative is x to n plus 1. Right. So, and the way that I kind of described this verbally last time was, think about what happens when let's do branching paths here. And Sebastian said this was the derivative, n times x to the n minus 1. Basically, the two things you do when you take a derivative using power rule are multiply that. So we're going to inverse that process. We're going to introduce this one by one. So any last questions on where 2/5? If we're okay with that, what is the antiderivative of negative x to the negative 1/2? So let's take it slow. So new exponent is going to be 1/2, right? All over 1/2. So I think what I have is this: 4 tangent x plus 2/5 x to the 5th minus 2 radical x. All right, are we good with this? I'm not. So one thing we have to look out for is that there's inherent ambiguity when you're taking antiderivatives. Are we good with this now? Any questions on how we got? Any questions on how we got here? Are you okay with the way we developed it?
Yeah.
So, and right.
Yeah.
Oh, you're good. So one thing I want to highlight here is this: if you're differentiating, let me say it this way. Give you a kind of a schematic diagram for this thing here. If I'm going to take the derivative of x to the power of n, first thing I'm going to do is multiply by n, and then decrease n by 1. But if I'm going to go the other way, what's the opposite of decreasing something by 1? Increasing it by 1. What's the opposite of multiplying by that exponent? So it really is an inverse process. Taking the two steps and doing the opposite of them in the opposite order. Which at this stage is totally, it's very typical to, to want to divide that by negative 1/2 instead of positive 1/2. Any other questions here? Go ahead. Yeah, of course. So x to the negative 1/2, like before we took antiderivative. So basically what I did is this. If I'm raising something, or if I'm taking a square root, what power is that equivalent to? And x is x to the what? Right. So when you're dividing, you're subtracting exponents, right? Yep. So yeah, 1/2 minus 1. Good question. Anything else? All right. So everything we've done up to now, we've found kind of this general antiderivative. Now let's look at a situation where we can do a little better. So first, let's find the general one. So I'm giving you f prime. Based on that, what is f of x going to look like? What's a function whose derivative is e to the x? Yeah, so that's one of those special characteristics of e to the x. It is its own derivative. And how about this other thing? 20 times 1 plus x squared to the negative 1. Does that look like something you've seen before? Is there a way to rewrite it, simplify it, break it down somehow? Okay. Is that true? Same thing? Do we know what function has this derivative? Yeah, arctangent, right? So one thing I'll remind you of is this. And really, over the last month or so, you've gotten really used to thinking about derivatives in one direction. Really, you're not using different facts or anything. You're just applying them in a different way. So what is the derivative of the inverse tangent of x? 1 over 1 plus x squared. So we're just going the opposite way. So then what is the antiderivative of this thing that we're looking at? It's 20 arctangent x. All right, we good so far? Nope. All right. So we're going to get rid of that because I have given you more data to work with. So how can I find out what that value of c is? Yep. So I know that f of 0 is equal to e to the 0 plus 20 arctangent of 0 plus c equals negative 2. What is e to the 0? 1. What is the arctangent of 0? So 1 plus c is negative 2. So c is equal to negative 3. So in this case, I can give you the particular, or we can give the particular antiderivative for this function. Any questions there? All right, let's go ahead and move on. All right, now I am giving you the second derivative. Sure. All right. So I want to find the function f, and I have the second derivative. So what's the first thing we need to do? All right, so let's just write down this antiderivative, and then I'll ask you a question about it. So 4x cubed, keep going, plus 3x squared. So what is this thing you just said? That's the first derivative. Now I'm going to pause there. Well, this. Right. So it really, I mean, the only thing you need for either of those three terms in front of it is you're all going to get fast at this, but not at the same rate as other people. So as long as you're understanding at this stage that the power rule is being applied there, you're on the right track. At some point, probably pretty soon, most of you will be able to just look at that and kind of write it down. All right, are we good so far? Good. No. Is that okay? I do need plus C. So remember, no matter what function I'm starting with. Function you have. What I mean by that is we have no way of getting from ethyl prime to that. Figure out. We have to do some work, basically to build one function at a time. So are we okay with this this expression for f prime? All right. What can we do with this thing? Okay. So x to the fourth plus x third to the third minus 2x squared plus c cx. No, oh no, definitely don't call them the same thing. So they we call it lowercase k. Doesn't really matter. But yeah, so a couple of things to point out there. It seemed like at least a couple people were content to just kind of leave that alone. But just a reminder, let's go back which is true of any constant, whether or not we actually know the constant is. So, this because you don't know. So you're saying the constant doesn't exist, right? Yeah. In reality, the constant always will exist. But when you say it doesn't exist, what are you assuming it's equal to? Zero. Right. So yeah, we don't know that the constant, whether the constant's equal to zero or not. So we have to prepare for the fact that it might not be. So, but it's not that it doesn't exist, it's just that it might be equal to zero. All right, so now that we have this, so we have the information we need to solve for C and D. Right. And it kind of seems like, yeah, I meant for one of those to be F prime, but we actually don't need that. All I do need is two pieces of information. So what's f of 0 equal to? F of 0 is equal to 4, which is really equal to D, right? Okay, so I'm going to go ahead and, okay, we'll go with that. What's f of 1 equal to? It's equal to 1 plus 1 minus 2 plus C plus 4, which is equal to 1. So what is C equal to? -3. Okay, so that allows us to rewrite or give a particular antiderivative here. Got x to the fourth plus x cubed minus 2x squared minus 3x plus 4. Any questions there? Or yeah, so I skipped a lot of stuff there. So let's. Are you sure? What do you see? Right. Okay. And when x is equal to 0, basically the only thing that doesn't go to 0 is d. That's d. So here's one thing I need to point out about C and D, or let's just ask this question. Look at this thing here. How many variables are there? Disagree. There's one variable. So C and D are not variables. They are constants. We just don't know. We didn't know what they were there. But once I find them, they're fixed. I get to just write down that they're equal to, like D is equal to 4 once I find that out. Any other questions here? I think that was it. Oh, no, it's not. Oh, I forgot. So we've talked a bit about the ideas of position and velocity and acceleration. How are those three things related to each other? In whatever order you want to put them. So velocity is rate of change of position. And typically when we say rate of change of something, we have to, okay, good. With respect to time. And Jordan, what was the other? Acceleration is the rate of change of velocity with respect to time. So first of all, are we okay with these two ideas, these two relationships here? So if velocity is the rate of change of position with respect to time, let's give the typical symbols to these. So we call it position usually S, velocity V, acceleration A. Is there a way to represent either one of these two sentences that Jordan gave us as, like in mathematical notation? Daniel? So velocity is the derivative of position. So velocity is equal to the derivative of position with respect to what? Right. So we said that, right? So we can say that V is equal to ds dt, or if you prefer, S prime of t. And hopefully that looks familiar. We've used this notation in the past, right? Okay. We say something similar about acceleration. dv dt, or d prime of t. Let me go a little further. Yeah, we can say that A is equal to S double prime of t. But now think about the way we've been talking, or what we've been talking about this section. What's another way that, for example, you could say the velocity and position are related? Thomas? Velocity is the antiderivative of acceleration, which really is not different. Are we okay with what I said there? Should I write it down? Yeah. Okay. And I'll say and antiderivatives. Those of you who are looking at these things in physics right now, or maybe in the past, do you use calculus or derivatives to deal with them? No? Okay. All right. Any questions about what we've talked about here? All right, let's go ahead and use it. So I have a particle that moves in a straight line, just back and forth. And all I'm giving you right now is its acceleration. I want to find a position function. So basically, I want to find where this thing is for any time t. So given the information I have here, take a second to read it if you need to. Well, given that information here, okay. So if I take an antiderivative of acceleration, sticking with our lowercase and capital scheme, what's that antiderivative going to give me? What's the antiderivative of 6t? 3, not x, but yes, 3t squared. Minus 4t. Say minus t? Oh, so let's hold on. I'll hold off on that for now. Let's just, let's call that the constant. And we know this is also equal to the velocity. Do I have enough information to figure out what that constant c is? Yeah. How do I do that? Yeah. One thing I'm going to caution you against is just because you know the initial something, it doesn't mean you can just charge ahead. We did an example like that today, but I'll just I don't want you to get too much of a false sense of security here. And I cheated, didn't I? So this gives us a velocity function of 3t squared minus 4t minus 6. Okay, what is the answer? So antiderivative of velocity is going to be, so give me that expression then. T squared plus c. Good. And I took the antiderivative of velocity, so that's going to give me what kind of thing? That's a position function. And do we have the information we need to get? And because I went through it the last time, what's going to happen if I plug it over? If I set t equals 0 in my position point. Basically, what's going to happen to all the non-constant terms? They're going to go 0, right? So S of 0 equals c, which is equal to 9. All right, so wants to finish this thing off. What's S of t equal to? There you go. So that's what we're asking for. So that now that I have no unknown constants, if I know how far, if I know like kind of what time, what instant I'm looking at this thing's position. Exactly. Any questions here? What's that? Okay. The what did? Oh, okay. So yeah, just a reminder, what am I using the capital letters to signify here? Antiderivatives, yep. Sebastian. Okay. Anything else? I'm gonna go ahead and skip this one. Actually, yeah. Okay, so that is all from 4.7 and all. That's chapter 4. So with the last like 20 minutes or so, let's dive into chapter 5. All right, so chapter 5 is called integrals, which may not be a word. We'll gradually build up to that. In the first section, I'm going to talk about how to deal with areas and distances. And just some motivating examples, like these probably aren't going to make a ton of sense to you right now, but this is kind of what we're working up toward. So if we have the graph of a function, can we find the area underneath that? Which is probably a phrase you've heard, like finding the area underneath the curve, things like that. This is something the integrals are equipped to do. We know the speed of an object at any time. Can we find the position of the object at any time? We did something a lot like that just now. Or we understand the growth or decay of a substance with respect to time. Can we find out how much stuff there is over time? So let's look at a kind of a generic example here. I want to find this thing. And like between those two vertical lines A and B, I want to find that shaded area. I don't have a nice formula for this thing. It's not a geometric shape that we recognize. So how could I find this area? Even if it's just going to be a rough guess, what could I do to help me get that? Thomas? Okay. So make a rectangle like how? How many? Just one? Okay. So I'm going to try to have one that's as tall as what I think the middle of this is. So how good of an estimate is this going to be here? Not really good, right? So yeah. So basically what I'm trading in accuracy for simplicity. I don't know how to find the area, whatever that shape is called. I know how to find it. Well, if I measure that height, then I'm basically done. Is there any way to make this a little better? Okay, so I'm hearing one change as more rectangles. So let's divide this thing up into, it's going to be 10. Does it matter that they're not all the same width? Not really. All I got to do is measure the sides and multiply, right? But basically what I'm doing here is, so this is not nearly as simple as what Thomas suggested, but what advantage does it buy us? A little bit more accurate. Really, I'm still just taking areas of rectangles, which is something I understand how to do pretty well. I don't think you need to see me draw all of them. Well, yeah. It's really small. How wide are they? And but why? So when you're taking the area of a like the surface area of a cylinder, is that what you're talking about? Even the volume of a cylinder, like why is taking the volume of a cylinder so easy? Yeah, it's a very, I mean, that's a shape we understand really well. This thing is strange. So yeah, what I'm doing here is I'm taking it and cutting it up into rectangles so I have a chance. But let's go back to this idea of us making these rectangles, you know, as narrow as I possibly can. I'm still finding the area of just rectangles, but how many am I going to have? Like a lot, right? And it's, I think, Saul, did you say infinitely many? Yeah. The tough thing about that is, you know, getting to infinity, that's kind of a hard barrier to cross, because if they're infinitely narrow, it's hard to quantify that width. And even though it's hard to quantify that, that's kind of what we're going to be ending up working toward. But basically what we're doing here, we're going to look at area in terms of this. We're going to look at area instead of, you know, this curvy shape here. We're going to just think of it as rectangles and try to work up to this area that way. So any questions on kind of what the motivation is so far? So that's pretty abstract. Let's go to something concrete here. I want to use 4 rectangles to estimate this area. So looking at our, you know, basic parabola y equals x squared on the interval from 0 to 1. I want 4 rectangles, and let's make them equally wide. So let's really, given what I have given you so far, I mean, you could do this any number of ways. I'm going to say this. I want to make the equally wide rectangles. And I want to sample at the right endpoints. So basically, starting from the right, so basically my first rectangle is going to look like this. Go ahead and draw. So how good of an estimate is this going to be? Not very good. And specifically, so it's going to be wrong, right? Correct? In what way is it going to be wrong? I'm going to overestimate, right? So I'm going to overestimate. But because I have decided to think about this in terms of more simple shapes, I'm at least going to be able to get a guess at it. So now let's get a guess at it. So based on, first of all, any questions on the way that like I said, I mean, so first of all, I'm saying, but yeah, I mean, if you're trying to do that, I'm kind of, I have a motivation for this that I'm trying to keep close to the vest right now, but we're going to treat this in terms of rectangles, and we're just going to use 4 subintervals, even though we've kind of all agreed that more would be more accurate. Well, let's go ahead and get our number here. So how can I find the area of these 4 rectangles? Okay, so let's say this area 1, area 2, area 3, area 4. Area 1 is there's all just length times width, right? Yeah. Or I guess I'll do base times height. How long is the base? How tall? So yeah, that's a good thing to think about now. So we need to know what these x values are, right? What are these x values with these hash marks? I don't think it's 0.125. 0.25, 0.5, 0.75, 1.0. So let's talk about how we got that. How did we find these x values here? Or I guess first we talk about this. How do we find the width of any one rectangle? I'm sorry, let me go back. So that was the question I asked first, though. I need to go back one step. How do we get, so all four of those rectangles have the same width, right? Yeah. How do we find that width? So how do we find the width of our entire interval? Okay. So right end 1, left end 0, dividing that by 4, you get 0.25. So I believe that our first one would be 0.25 times 0.25 squared, right? Which is going to come out to, I'll write down the fraction. I'll let one of you, why is it squared? Yeah. So how tall is that? The area of one rectangle. So it just, remember, all of my heights of my rectangles are going to come from whatever the function is at the right end of that little subinterval. So this point right here is going to be 0.25 and 0.25 squared. Yeah, why am I squaring? Yeah, so the function's y equals x squared, right? So yeah, this is not, sorry, this is the function we're looking at. I'm trying to find the area. Okay, so y equals x squared, just a reminder. So we got the first area. Area 2 is going to be what? Times what? 0.5 squared. And the third one? So yeah, basically, it's a fixed width for all these little subintervals. And if anybody wants to add those up for me, 0.25 times 9/64. And this last one's going to be 1/4. You know, let's just to make these things easier to think about, let's get an area now, like in decimal form. If someone can give me 4 decimal places, that'd be good. Think about, so if I think those 4 small areas, I want to use them to find the larger area. What do you think? Am I adding or dividing? I'm adding them all. Someone have a number for me? I'm going to iPhone this. We got 0.4875. That sounds more reasonable and more familiar. And I'll tell you more about why I do that when we get to the end here. But are we okay with this? We already said this number was going to be wrong and wrong high, right? But are we okay with how we got it? Okay. What's that? I could. Oh no, so I tend to leave it up. I mean, we're dealing with unitless area. I mean, the base length and the height have no units. So, but yeah, if you want to call it unit square, that's good too. Any questions on how we got this? All right, so one thing we agreed on was that more rectangles is better, right?
Yeah.
So let's do it double the amount of rectangles here. So I'm going to draw these in real quickly, but I'm way off on the width, aren't I? That's okay. And the height. Jeez. So based on what we just did, do I need to really draw all these out for us to be able to find these 8 areas?
Yeah.
So one thing we should talk about is this. What's the width going to be this time? It's going to be half what it was, right? So we're taking the same interval and we're cutting it up into twice as many pieces. So now we're going to find 8 areas. But let me ask a couple questions before we get a number here. But I don't know if we'll have time to finish, but we can at least talk about what's important. Based on the rectangles that I would draw there, that we're going to actually represent this area with, is it going to be exact? Is it going to be perfect? Is it going to be an overestimate, underestimate? Any way to tell? It's going to be an overestimate. So here's what we're predicting. Still wrong. Overestimate. How do you think it'll compare to the number we just got using 4 rectangles? So will it be smaller or larger than our last? So it'll be smaller than 4 subintervals. Here, Faye, you have a question? Yeah. Yeah, that's something else you can do too. And I think it'll make why I'm doing this. Yeah, just to kind of, you can use the middle, you can use lots of ways of applying rectangle is one way, and you can also see trapezoid, other geometric shapes. We'll finish getting that exact number or that estimate next time. Any questions before we go? So you guys jumped the gun. Can we get the area of these 8 rectangles? Let's do it and we'll all go. How do we find the area of the first one? Yeah. Right. So if you recognize the pattern, you're free to just jump at this. In fact, I might do that now. All right, I got area is 0.3984. So I think our predictions came true, right? We still know we have an overestimate just by visualizing what those rectangles look like. We think that if we keep doing smaller and smaller rectangles, we'll get closer and closer to the truth, but we're not there yet. Any questions? All right, everybody, have a good weekend. I'll see you Monday.